so that we'll go to the exact objective of this project. So moisture sensors exactly, they are like electronic devices that normally measure soil water content, and soil water content can be like represented in like different forms. Mostly like we prefer the volumetric ratio, but they can also be represented in mass ratio. And volumetric ratio, they mathematically it is defined as volume of water present in the volume of soil. Bulks, and particularly we represent that in percentage, and we call it percentage volumetric water content. And that equation can, as you can see, equation number 1, the term called BD, it is called bulk density. That's just the ratio of density content. And when we rearrange this equation, we end up getting that bulk density term. I'm just focusing on bulk density term because we face a lot of issues with this particular term while doing our tests. And this is a MATLAB plot, like a simulation of how the bulk density can affect the volumetric water content measured by the soil moisture sensors. So as you can see on the x-axis, we have the mass of water represented in terms of gram, and y-axis we see bulk density represented in gram per cubic centimeter, and the g-axis represents the volumetric water content. The g-axis, what we get volumetric water content, is based on the equation number 1. And from this, this simulation was basically done for like a standard mass of soil for 1,000 gram of soil, and it was done mostly for sandy loam Texas soil because our whole test was focused on sandy loam Texas soil. And we did this for bulk density in the range of from like 1 to 1.4 gram per cc. The reason for that, because one paper that based on USD and RCS tells that ideal bulk density for growth of the plant is less than 1.4 gram per cc. And from this, we can clearly see that we calculated the slope and how the bulk density and how the mass can affect the measured volumetric water content from the sensor. And we can clearly see, if you can see this term here, we can see the slope being 0.1 more for bulk density. That shows that bulk density has like, it can affect the readings from soil moisture sensors tremendously if it is not taken care of. So the compaction of the soil, it can affect the reading of soil moisture sensors. So how these soil moisture sensors make measurement? As I already told, these are electronic devices, so they have some kind of parameters. That's electronic parameters. They change based on the amount of soil water content, and those parameters like electrical resistance or electromagnetic pulse, time travel, these things are measured and they are calibrated based on the amount of soil water content. So that's how we measure amount of soil water content. And these are some of the most widely used soil moisture sensors. Among these, which we used this and this watermark from barometer and baseline for our testing results, which I'll talk about this a little bit in detail. So why do we use soil? Why do we care for soil moisture sensors? We care for soil moisture sensors because they help us schedule our irrigation in an efficient way and helps to save our water, and also it can simultaneously reduce the cost for irrigation and also save water and energy simultaneously. Now we can use this for agriculture as well as we can use this for landscape irrigation. Our whole focus is on landscape irrigation. So normally, let me give you a little bit background about what are the issues that we are facing with landscape irrigation. Like US EPA says that roughly in the United States, every year we use like 9 billion gallons of water for landscape irrigation, and out of that 50% is just goes wasted because of inefficient irrigation design. And moreover, although based on this, we have like, in addition, we have drought issues going on, so we are forced to like make use of efficient irrigation. So for that, we have to go using soil moisture sensors. But since we have a lot of soil moisture sensors, we don't have any federally standard existing to show how these soil moisture-based control technologies, how they are efficient there. So that's why this whole project focuses on like because of those inability of lack of this standard, the US EPA, they released a draft notice of intent in May 2013 to like introduce a draft for the soil moisture-based control technologies. And ASAP, the Committee of American Society of Agriculture and Biological and Agriculture Engineers, they are developing two standards because of this, S633 and S627. S627 is mostly focused on weather-based or soil moisture-based landscape irrigation control, and S633 is for the one that I'll be talking today. And this whole project was done to demonstrate a testing methodology for establishing S633 standard, as well as the whole topic says how these soil moisture sensors behave with drying cycle of soil. Baseline sensors, water take is 100 by sensor, the model water take is 100 and aerometers watermark 200 SS. These are the two moisture sensors as I told before that we prefer using these because these two are contrastically based on two different technologies. One is based on resistance while other one is based on time domain transmission. And just to give you a little bit background, technical background, the time domain transmission basically is nothing but we send a pulse of signal from the sensor blade, and when it is installed in soil, based on the amount of water available in the soil water content, the travel time is measured, and it calculates the travel time and thus calibrates based on soil water content. That's how it measures. And this is the equation, we call it top equation, that is used based on the travel time, and it determines the relative permittivity, which we call for the moisture sensors, we call it as the equivalent dielectric, it's called apparent permittivity, which is represented by Ka, and we just put this in top equation to get the volumetric soil water content. And we did a MATLAB simulation for this to see how these terms like permittivity and how the travel time, they can affect the change in volumetric water content of the soil. And this is how, I'll just go a little bit slow for this one. This is on the axis you see travel time in second and volumetric water content. So as the travel time for one sensor, if it takes more time, then definitely that represents like it's representing there is more presence of moisture in the soil. So this is how it behaves. And more travel time also represents a more apparent permittivity or relative permittivity, and that ultimately results in higher soil water content. And this is a MATLAB simulation of water irrigation with respect to changes in problems. So let's say we have different problems of moisture sensors. Some can be smaller, some can be like longer. And based on the problem, so it's just a simulation of seeing how the probe length and how the travel time simultaneously they can affect changes in the soil moisture content represented by the sensors. And I'm just showing one example over here for on the x-axis, as we see, like the travel time is like almost 1 nanosecond. Here, 0.9695 nanoseconds roughly represents 31% of volumetric water content. So what the other sensor was by Rometer's watermark 200 SS. It is based on different technology called resistance, and resistance is the electrical output given, but it doesn't give volumetric water content, rather soil watermetric potential. That is another way of representing moisture content present in soil. And the output resistance measure given by this electrical resistance that corresponds to the amount of available water content. And because more available water content will represent the different amount of water present in soil represents different soil water potential, and that is how we calibrate this implementing SOX equation. And this is how the measured metric potential by watermark 200 SS is implemented to get in the SOX equation to get the amount of metric potential. So it measures the amount of resistance from the sensor, and then it plugs into the SOX equation. In both of these, equation number 4 and 5, and then we get the metric potential. And this is just a MATLAB again simulation how this measured water potential varies depending on the electrical resistance. How let's say with different temperature and different electrical resistance measure how our water potential, metric potential changes. So I have just plugged. I can show you like this point here. You see. At 21 degrees centigrade with this, because all of our test was in our lab condition, environmental control. We did this testing at 21 degrees Celsius. And it was 11 kilo ohm measured, we get roughly minus 61.60 centibar of metric potential. And this is just a simulation of equation number 4 and 5. So what are the materials used for this what do you call this whole study? We use like 3 watermark sensors, 3 baseline sensors, and we used DI water. The whole test was performed at 0 EC, and we used 2 containers, different size containers. One was rectangular and another was cylindrical container. And we use a weighing scale as well as a weed control paper, and and also we use this little thing over here called tensiometers, and these were used just to get a reference point for those watermark sensors. I'll talk about, and this is how. Give me a second. So this is one by baselines by sensor, second, third. They were installed in this way, like the way I'm moving my cursor, and they were packed in the soil, and they were placed over a scale. I'll talk about the testing methodology later. The watermark sensors and tensiometers, they were put in this cylindrical container, and the tall ones, these were the tensiometers, and these small ones are the watermark 200SS sensors. And this is just the flow chart of how the whole test was done. So the first thing we do is like we pack the soil and we calculate the bulk density based on the container volume and the amount of mass of soil packed inside it. We pack this with the all the three sensors in each container. The baselines in rectangular and the aerometer watermark in the cylindrical container, they were packed. And then we applied water using drip emitters. Circular drip emitters for the cylindrical container and the regular drip emitters for the our baseline sensors. And then we leave it, we saturate the soil, we normally water for like an hour, and we left it to dry, and once the whole water gets run up, we leave it for like 24 hours, and then we measure the amount of weight, and we calculate volumetric water content at that point, and we call that as field capacity. But we found some issue of calling field capacity, so we also call it as container capacity. So we take that as a reference point, and then after every day we measure like every day we take 2 readings for next 10 days, and we try to compare it with the previous measured volumetric water content, and we try to see something called a depletion percentage, that how much water has been decreased with time. And based on that, we plot graph, and our whole testing methodology, our whole data analysis is based on that. Now, what are the parameters that we did data analysis on? We did data analysis based on variance. Something called variance is a statistical method. Now it gives us like how those three sensors are like varying from their mean values with each depleting cycle. Similarly, and the second parameter was repeatability. Now we did the testing for not only one cycle, but we did it like for all 4 cycles, ignoring the first cycle. Because when we prepared the soil, by baking them and grinding them, the soil structure gets disturbed. So we had to ignore the data we obtained from the first cycle. From the second and third and fourth cycle, we test the repeatability. That's why we introduce the term repeatability test, so that we see how much repeatable this sensor data are from second, third to fourth one. And the test of repeatability also shows us the regression. From that curve we get to something called regression value, and that also gives us the measure of precision, how precise those sensors are. So variance, how much variability there is in each cycle among the sensors, and how repeatable they are from one cycle to next cycle to third cycle, and how precisely they give the reading. So these are the parameters for our data analysis. Now we move to the results and discussion. This graph might look a little bit awkward. I will just say like, in the these results are for baseline sensors. First we'll talk about this, and it was a MATLAB test plot, and we did a test of. In the second cycle, as we ignored the first cycle, this is a test of variance, and as you see here, we got a maximum variance of 6.043 per cycle 2 and 5.763 per cycle 3. And it was found to be the lowest in the 50 and 60% range. So when the soil were wet, they normally varied more, and as the soil dried, the variance it decreased, and it was found to be lowest in the 50 and 60% depletion zone. Same thing in the third cycle, we found similar result. The variance was found to be minimum in the wet end, whereas it was found to be more in the dry end. And this is the test of repeatability and the test of precision. We found for the sensor number 1, we find a regression value of 0.7562, and for the sensor number 2, 0.81 and 0.96 for sensor number 3. Out of this, sensor number 3 was found to be highly repeatable, but they cannot be equally repeatable. So sensor number 2, as I said, it was found to be highly repeatable, and hence it was also highly precise compared to sensor number 1 and 3. And this is for the Aerometer 200SS sensor. Thank you. I still have 5 minutes. So this is So this is like this is for the this is a variance test for sensor number 1 and 2. I mean cycle number 2 and 3, because we ignored cycle number first. So here also we see the same thing, pretty much same thing, but maximum variance was found to be 13 in the depletion, kind of little bit not the same as I would say like the TDT sensors, the baseline sensors, because they showed more variance in the wet end, but this showed like what you call more variance towards the dry end in the aerometer side. And in cycle number 3, the variance of these sensors was like 0.33 up to 30% depletion. So, and the maximum variance was 4 in 40. So again, we see a little bit trend is like in the towards the dry end aerometer watermark sensors were little bit they had like more variability among themselves from their mean value. And for the in cycle number 3 also same thing, and the variance was found to increase between 50 and 60%. So unlike the baseline sensors which has more variance in the wet end, the watermark sensors had like more variance towards the dry end, if you can see. And this is the test of repeatability for watermark sensor number 1, 2, and 3. And these were found to be comparatively like more repeatable and more precise, unlike the baseline sensors. However, the baseline sensors were found to have like consistent variance with each drying cycle. So even though they had a little bit higher variance, but they were like very linear compared to unlike the watermark sensors. But watermark sensors had like they were like more reliable outside. And so the future work, why I'm talking about future work, because this is undergoing process. We are still working on this, and we are finding some kind of issues. The major issues are being with our wetting pattern, the way we are wetting, and the compaction. So we are having issues with those. We are working on that, the whole committee of S633. We are working on that, and we're trying to come up with the what it calls fruitful result as soon as possible. And we'd like to thank the US EPA, Charles Swanson here, Dr. Jukes, and our whole CIT members, and Janet. And any questions, please? And Mary within time. Wow. That's a good question, I would say, because we chose rectangular container for baseline sensor white, and we chose cylindrical for So based on manufacturer's recommendation, these sensors they need to be packed in such a way that we have like, let's say, like at least an inch of soil on top of them, and at least an inch of soil at bottom, and they have something called sphere of influence because they're electrical sensors, so they emit some kind of electrical, let's say, pulses. So they should not like, let's say we have a longer sensors, let's say 6-inch sensor. So based on that, we have to make our decision what kind of container we are going to use, so that we can pack it good enough so that the sphere influence doesn't get affected by those metallic cylinder from the surrounding areas.
So the sphere of influence in each container was appropriate to the individual sensor?
Right, so we made sure our decision was based on manufacturer's recommendation, because when they design sensor, they tell us like, hey, they shouldn't be like in very close proximity to each of them, and also shouldn't be in close proximity to some metallic case that can affect their readings drastically. So we have to make a decision based on manufacturer's recommendation.
And also, just to add to that statement, everybody started with the cylinder containers, but it wasn't the manufacturer recommendation that the sensor be installed vertical. The sensor had to be installed horizontal, so that sensor did not fit for that purpose in the cylindrical container.
Would it be better to install each sensor in a separate container? Like have them as the 3 baseline sensors, but each in a separate container, similar, everything similar, same thing for their own?
Right, I mean, we can do that. We can definitely do that, let's say like in 3 different containers of one sensor in each, right? Right, we can do that. But we are trying to reduce the variability, like the parameters that can affect. So we try to put them like all 3 in the same one, so they all have the same environmental factors affecting in the same way. Because let's say if I put one sensor in one container, the other in the other, so maybe there is an extra increase of variability we are introducing to our data point readings. Maybe that soil is not equally packed in that container, just it might not have the same bulk density as this one. And even slight change of bulk density can affect our reading drastically, because as I think I showed you in the beginning slide, that was the whole idea of I introduced you to the this simulation thing that this bulk density can cause like more. Where is that? I think it was here. So bulk density has like really, if you see here, increase in your bulk density results in greater increase in volumetric water content as compared to increase in mass of water by itself. So that's the reason why. So we have to, we recommend, I mean, so far we have come up with the thing that we have to, it's better to do it in the same container for all the three sensors rather than putting it in different containers.